of the products, tau of p square minus zeta power z plus zeta power minus z plus 2 times p power 11. Here zeta is n plus 1 root of unity, e power 2 pi I by n plus 1, and delta n is 0 or 1 depending on whether n is even or not. By the Delign's bound, and modulus of tau of p is less than or equal to 2 into p power 11 by 2, and using the fact that tau of p is not equal to 0, we get tau of p square divided by p power 11 is a rational number, but it is not an integer. Since we know that zeta power z plus zeta power minus j plus 2 is an algebraic integer, I'll also define what is an algebraic integer shortly. This is an algebraic integer, but tau of p square divided by p power 11 is a rational number which is not an integer. Hence, each term in the product is not equal to 0. And by our assumption, tau of p is not equal to 0. So we get tau of p power n is not equal to 0, a contradiction. Hence, we conclude that the lemma's conjecture is equivalent to the fact that tau of p is not equal to 0 for all primes p. In 1981, Serre proved that tau of p is not equal to 0 for almost all primes p. Almost all in the sense, the ratio of the primes less than or equal to x, for which tau of p not equal to 0, to the number of primes up to x converges to 1 as x tends to infinity. And by prime number theorem, we know that number of primes up to x is asymptotic to x by log x. This result of Serre was generalized in a wider context by Gunn and Osterle in 2015. As a strengthening of the lemma conjecture, Atkin and Serre asked the following question. Given any epsilon positive, whether there exists a positive constant C of epsilon depending on epsilon such that the modulus of tau of p is bounded below by the constant depending on epsilon times p power 9 by 2 minus epsilon for all primes p. Concerning the lower bound for the values of the term functions at the integers, we have the following result of Murthy and Shore. They prove that there exists a positive constant C such that for all the natural numbers n such that tau of n is odd, then modulus of tau of n is greater than or equal to log n to the power c. In a recent result, Gaffney, Thorner and Wang proved that for almost all primes p, the modulus of tau of p is strictly greater than 2 into p power 11 by 2 log p divided by square root of log p. By using the Jacobi's triple product identity, we can show that the summation of tau of n q power n is equal to 1 to infinity is congruent to summation m is equal to 0 to infinity q to the power 2m plus 1 whole square modulo 2. This implies that tau of n is odd if and only if n is an odd square. In particular, this shows that tau of n is divisible by 2 for almost all integers. And Ramanujan also conjectured that for almost all integers n, tau of n is divisible by 691. This was verified by Watson in 1935. This result was strengthened by Serre. He showed that tau of n is divisible by d for almost all integers given any natural number d. This result was further strengthened by Murthy and Murthy. They showed that for almost all integers n, tau of n is divisible by a power of t, where t is equal to integer part of delta log n. Here delta is a positive constant which depends on d, and observe that the power t goes to infinity as n tends to infinity. In particular, this result implies that number of prime factors of tau of n is at least the number of prime factors of d for almost all integers n. Since d is an arbitrary natural number, this implies that the number of prime factors of tau of n is large for almost all integers. Let us denote omega of n by the number of distinct prime factors of n. And also we set omega of 0 is equal to omega of plus or minus equal to 0. For example, omega of 2 is equal to 1. Omega of minus 4 is equal to 1 because it's divided by only prime 2. And 3,37,500 divisible by the 3 primes 2, 3, and 5. So the omega of 3,37,500 is equal to 3. If n is a non-zero integers, since each prime is greater than or equal to 2, so n is greater than or equal to 2 per omega of n. So by taking the logarithms, we have the trivial bound for the number of prime factors of n. Omega of n is less than or equal to log n by log 2. In particular, one can show that the number of prime factors of n is at the most a positive constant c times log n divided by log n. In 1907, Hardy and Ramanujan proved that the number of prime factors of n has normal order log n. That is, for any epsilon positive, the ratio of the integers less than or equal to x such that the omega of n divided by the log n minus 1, the difference is less than epsilon divided by x goes to infinity, goes to 1, sorry, it goes to 1 as x tends to infinity. Now the question is whether tau of n take the prime values or the prime power. In both these cases, the number of prime factor of tau of n is equal to 1. Lemma in 1965 proved that tau of n is composite if n is strictly greater than 1 and less than or equal to 63,000. In fact, he showed that the value of the tau function at 63,001 is actually a prime number. By the result of Murthy, and Shore, it follows that given any odd prime p, the set of natural numbers n such that tau of n is equal to prime p is a finite set. Lazarus and Rosier proved that tau of n equal to plus or minus 1 has no solution for n greater than or equal to 1, n strictly greater than 1. Since tau is a multiplicative, so if n is equal to product of pi to the power ai, then tau of n is equal to product of tau of pi to the power ai. Since tau of n is equal to plus or minus 1 has no solution for n greater than or greater than 1. So if tau of n is a prime, then n must be a prime number. In fact, they proved that if tau of n is a prime number, then n must be of the form p power q minus 1 with p and q are odd primes and p does not divide tau of p. In a recent archived paper, Balakrishnan, Crick, Ono and Zai proved that if tau of n is an odd prime power, then n must be a prime power. In fact, they show that given any odd prime L, if tau of n equal to plus or minus L power m, then n must be of the form p power q minus 1 with p and q are odd primes and q divides L into L square minus 1. Now, by using the Dellin's bound, modulus of tau of n less than or equal to d of n into n power 11 by 2, where d of n denotes the number of divisors of n, and using the upper bound for the number of prime factors of n, we have the following upper bound for the number of prime factors of tau of n. Omega of tau of n is less than or equal to some positive constant times log n divided by log n. As mentioned earlier, it follows from the result of say that given any natural number m, the number of tau of n has at least m prime factors for almost all natural numbers n. In 1984, Murthy and Murthy proved the modular analog of the result of Hardy and Ramanujan. They proved conditionally under the generalized Riemann hypothesis that number of prime factors of tau of n has normal order half log n the whole square. In 2006, Luca and Spellinky proved a unconditional lower bound for the number of prime factors of n. They show that given any epsilon positive, the number of prime factors tau of n is at least 1 minus epsilon times log n for infinitely many natural numbers n. Here, we prove the following improvement. We show that for any epsilon positive, tau of n has at least 2 power 1 minus epsilon log n divided by log n prime factors for infinitely many natural numbers n. In fact, we show that given any epsilon, there exists infinitely many natural numbers n such that tau of p power n has at least 2 power 1 minus epsilon log n divided by log n prime factors for almost all primes p. The above theorem holds if the lemma conjecture is true, then the above theorem holds for all primes p. We also remark that by the result of Murthy and Murthy, we have the following upper bound for the number of prime factors of tau of n. Omega of tau of n is bounded above by half plus epsilon times log n the whole square for almost all integers n subject to generalized Riemann hypothesis. We unconditionally produce a infinite subsequence Ni such that tau of Ni has at least 2 power 1 minus epsilon log Ni divided by log Ni prime factors. Observe that 2 power 1 minus epsilon log Ni divided by log Ni is much higher than log n square if n is large enough. This in particular shows that the upper bound 1 cannot hold for all but finitely many natural numbers n. We also generalize this result in the general context of the modular forms. So let's recall a few facts from the theory of modular forms. Let SL2Z denote the 2 cross 2 integer matrices with determinant equal to 1. It is called a unimodular group. It is generated by the two matrices T and S. T is equal to 1, 1, 0, 1, and S is equal to the matrix 0, minus 1, and 1, 0. There is an action of SL to Z on the upper half plane given by the Mobius transformations. The matrix ABCD in SL to Z acting on Z gives AZ plus B divided by CZ plus D. In particular, the T acts on upper half plane by translation by 1, and S acting on Z gives minus 1 by Z. A fundamental domain for this action of SL to Z on the upper half plane is given by the blue colored graded region here. Let K be an integer. A modular form of weight K for SL to Z is a holomorphic function on the upper half plane satisfying the following two properties. The first one is the transformation property for any Z in the upper half plane. For any matrix ABCD belongs to SL to Z, f of AZ plus B divided by CZ plus D is equal to CZ plus D to the power K times f of Z. Since we know that SL to Z is generated by two matrices T and S, so this property is equal to saying that f has period 1 and f of minus 1 by Z is equal to Z power K times f of Z for every Z in the upper half plane. The second property is that f has a Fourier expansion of the form f of Z equal to summation n is equal to 0 to infinity summation f of n q power n. Here q is equal to e power 2 pi I z, z belongs to the upper half plane. The coefficients af of n are called the Fourier coefficients of f. Let me also introduce the slash notation. Let GL2 plus R denote the invertible real matrices with a positive determinant. We define f slash gamma at Z to be determinant of gamma to the power k by 2 times CZ plus D to the power minus k times f of gamma Z for Z in the upper half plane. With this notation, the first property of the modular form is equal to saying that f slash gamma is equal to f for every gamma next to Z. A modular form f is called a curse form if f of 0 is equal to 0. For simplicity, let us denote SL to Z by gamma. Let mk of gamma be the set of all modular forms of weight k for gamma, and sk of gamma be the set of all curse forms of weight k for gamma. Then mk of gamma and sk of gamma are 5-dimensional vector space or the set of complex numbers. In fact, the space of curse forms is a Hermitian inner product space with a Peterson inner product given by the following double integral over the fundamental domain F. For any two curse form F, G, inner product F, G is equal to double integral over the fundamental domain of the integrand y power k f of z, g of z conjugate divided by y square. If okay, on the space of curse forms, there are special linear operators called the Hecke operators. Let me introduce what are called Hecke operators. Let M be a natural number and let Xm be denote the 2 cross 2 matrices with integer entries and determinant equal to M. On this, the SL to Z acts on Xm by left multiplication, and it turns out that the number of orbit for this action is a finite. For a natural number M, the mth Hecke operator is defined as follows. If for a modular form F, Tm of S equal to the constant m power k by 2 minus 1 times summation f slash gamma, where gamma varies over the representative for the orbits for this action of SL to Z on Xm. If F is a curse form, then its image under the mth Hecke operator is also a curse form. That is, Hecke operators take a curse form to a curse form. Hence, if you restrict the Hecke operator to the space of curse form, they are linear operators. It is well known that Hecke operators commutes with each other and they are Hermitian operators. That is, given any two curse form F, G, the inner product of Tm of F, G is equal to inner product of F and Tm of G. Hence, the space of curse forms has a basis of simultaneous eigenfunction for all the Hecke operators. These simultaneous eigenfunctions are called Hecke eigenforms. If F is a Hecke eigenform, then the first coefficient is non-zero, so we can normalize it. A Hecke eigenform is said to be normalized if f of 1 is equal to 1. If F is a normalized Hecke eigenform, then F is an eigenfunction for the Tm with eigenvalue equal to the m Fourier coefficients. These coefficients are real algebraic integers, and the smallest field containing all this Fourier coefficient is a finite extension of Q. Before going further, let me recall a few facts from the algebraic number theory. A complex number alpha is called as algebraic number if there exists a non-zero polynomial with integer entries such as the f of alpha is equal to 0. It is called as algebraic integer if f is a monic polynomial for which f of alpha is equal to 0. A number field is a finite field extension of Q. Let OK be the set of our algebraic integers in K, then OK is a Dedekind domain. So if you take any non-zero proper ideal in OK, it factors into product of prime ideal as here. Let I be a non-zero ideal in OK, then it has a finite index in OK. We define the norm of the ideal to be its index in OK, and we denote it by nk of I. Let F be a normalized Hecke eigenform with Fourier coefficients f of n. As mentioned earlier, f of n are real algebraic integers, and the smallest field containing these coefficients kf is a number field. Let OKF be the ring of integers of kf. Suppose f of n is not equal to 0 and it is not a unit in OKF, then the ideal generated by the OKF factors into product of prime ideals. We define omega f of fn to be equal to r, the number of distinct prime ideal divisors of f of the ideal generated by f of n. We also set omega f of fn equal to 0 if f of n is 0 or a unit in OKF. With this convention, we follow the following theorem. There exists a subset Pf of primes of density 1 such that for any prime in Pf and any epsilon positive, there exist infinitely many natural numbers n such that omega of f of n is at least 2 power 1 minus epsilon log n by log n. So one of the principal tools used is the properties of the Lucas sequences. A pair of algebraic integers alpha comma beta is called a Lucas pair if alpha plus beta and alpha beta are non-zero co-prime integers and alpha by beta is not a root of unity. Given a Lucas pair alpha comma beta, the corresponding Lucas sequence un is defined as follows. Un is equal to alpha power n minus beta power n divided by alpha minus beta for n greater than or equal to 0. For example, if you take alpha is equal to 1 plus root 5 by 2, beta is equal to 1 minus root 5 by 2, we get the Fibonacci sequence Fn. Fn is equal, F1 is 1, F2 is 1, and F3 is 1 plus 1, 2, F4 is 2 plus 1, 3, F5 is 3 plus 2, 5. So Fn is actually equal to Fn minus 1 plus Fn minus 2. A prime number P is called a primitive divisor of Un if P divides Un, but it does not divide U1, U2, and Un minus 1 and alpha minus beta the whole square. In 1974, Sunil proved that there exists an absolute constant N0 which is positive, such that given any Lucas pair alpha comma beta and any natural number n greater than N0, Un has a primitive divisor for n greater than N0. This result was made explicit by Stewart, who showed that one can take N0 to be e power 452 times 2 power 67. The best possible result is due to Bilu, Handrot, and Voiter. They proved that N0 is precisely equal to 30. Now we come to the second part of our talk, the radical of Fourier coefficients of the modular forms. For any integer n, let the radical of n is equal to product of prime divisors of n. We also set q of 0 is equal to q of plus or minus equal to 0. For example, q of 2 is equal to 2 and q of minus 108 is equal to 6. We have the Delign's bound. The absolute value of the p power n is less than or equal to n plus 1 times p power 11n by 2. Suppose tau p power n is not equal to 0, then we have the trivial upper bound for the radical of tau p power n. The radical of tau p power n is less than or equal to absolute value of tau p power n, which is less than or equal to n plus 1 times p power 11n by 2. Suppose tau p is not equal to 0, let v tau p be the largest power of p, which divides tau of p. By using induction, we can show that the power of p in tau of p power n is exactly equal to n times the power of p in tau of p. If v tau p is not equal to 0, then we have the following upper bound for the radical of tau of p power n. The radical of tau of p power n is less than or equal to absolute value of tau of p power n divided by p power n v tau p minus 1, which is less than or equal to n plus 1 times p power 11 by 2 minus v tau p plus n times n plus 1. So in particular, by taking the logarithm, we have the log of the radical of tau of p power n is less than or equal to a positive constant c times log p times n. As a consequence of our bounds on the number of prime factors of tau of p power n, we prove that given any epsilon positive, there exists infinitely many natural numbers n such that the log of the radical of tau of p power n is greater than or equal to n power 1 minus epsilon times log 2 divided by log n for almost all primes p. So note that here the power in the upper bound, the power of n is equal to 1. Here we have the lower bound with power equal to log 2 by log n. This is a little of 1. This result can also be deduced from the work of Stewart on the radical of Lucas sequences. In our study of the radicals, ABC conjecture naturally enters. Massel and Oesterle conjecture that given any epsilon positive, there exists a positive constant which depends on epsilon such that for any mutually co-prime integers a, b, c with a plus b is equal to c, the maximum of the absolute values of a, b, c is bounded above by the constant depending on epsilon times the radical of a, b, c to the power 1 plus epsilon. Frey proposed a number field analog of the ABC conjecture. So before stating the conjecture, let us recall few facts from the algebraic number theory. Let K be a number field with degree of extension equal to n. Let sigma 1, sigma 2, sigma 1 be the embeddings of the K into C, the injective homomorphism into C. Then we know that the ring of integers of K, OK is a finitely generated Z module. There exists beta 1, beta 2, beta n such which are algebraic integers such that OK is equal to Z beta 1 plus Z beta 2 plus Z beta n. The discriminant of the field K is defined by the square of the determinant of the n cross n matrix whose ijth entries is equal to sigma j of beta I. And this is independent of the choice of the basis beta 1, beta 2, beta n. For example, if you take K is equal to Q of I, here the I is square root of minus 1, here the I is integer. Then Q of I has degree 2 over the Q. There are two embeddings of Q of I into the set of complex numbers. One is given by identity, second is given by the complex conjugation. Here, OK is generated by I over Z. The discriminant of K is the square of the determinant of the matrix 1, 1, I minus I, which is equal to minus 4. For a non-zero algebraic number alpha, the height of alpha is defined by the following expression. Height of alpha is equal to 1 divided by the degree of extension times summation I is equal to 1 to n, the log plus of modulus of sigma of alpha. Here the log plus is equal to maximum of 0 and log plus summation over the primordials maximum of 0 minus valuation of p at alpha times log of norm of p. The valuation of p at alpha is the power of p, the ideal factorization of the ideal generated by alpha over k. And this definition of height of alpha is independent of the field k. For example, height of plus or minus 1 and height of plus or minus 1 are equal to 0. And height of 1 plus root 2 is equal to half times log of 1 plus root 2. Height of alpha, height satisfies the following properties. For any two non-zero algebraic numbers alpha comma beta, height of alpha beta is less than or equal to height of alpha plus height of beta. Height of alpha plus beta is less than or equal to height of alpha plus height of beta plus log 2. And height of alpha power n is equal to absolute value of n, the height of alpha for any integer n. We also know that height of alpha is 0 if and only if alpha is a root of unity. Let me give a sketch of the proof. Suppose if alpha is a root of unity, then the conjugates, the sigma of alpha has more absolute value 1. So the log plus of modulus of sigma of alpha is equal to 1. So therefore the first sum is 0. Since alpha is a root of unity, so it's an algebraic integer. So valuation p at alpha are greater than or equal to 0. So therefore the second sum is also 0. Hence height of alpha is equal to 0. In the other direction, if height of alpha is equal to 0, so if height of alpha is equal to 0, we get, so in particular the second sum is 0. So therefore this sum is 0. So therefore the valuation of p of alpha are greater than or equal to 0 for every prime ideal. So this implies that alpha is an algebraic integer. Alpha is an algebraic integer. Since the first sum is equal to 0, this implies that the log plus of the modulus sigma of alpha is equal to 0. This implies that the modulus of sigma of alpha is equal to 1 for every I between 1 and n. So therefore, in order to prove that alpha is a root of unity, we use the fact that set of algebraic integers in OK such that the modulus of sigma f beta is equal to 1 is a finite set. To show this one, so if we consider the minimum polynomial of beta, it has a bounded coefficients. So we can, I think it's modulus of sigma of alpha is less than or equal to 1 because of log plus. So here is also modulus of sigma beta is less than or equal to 1. So we consider the minimum polynomial of beta. So minimum polynomial is the smallest degree polynomial, irreducible polynomial with integer coefficient such that f of beta is equal to 0. The coefficients of alpha can be expressed in terms of the modulus of sigma f of beta. Since modulus of sigma beta is less than or equal to 1, so therefore the minimum polynomial has bounded coefficients. So there is only finitely many choices for the minimum polynomial, and each minimum polynomial has finitely many roots. So therefore, number of such beta has to be finite. So therefore, the set S is a finite set. Since modulus of sigma of alpha is equal to 1, so therefore modulus of sigma of alpha to the power r is also less than or equal to 1 for any natural number. So in particular, this shows that the set alpha power r belong to natural numbers n is a finite set. So we get for some r less than s, alpha power is r is equal to alpha power s. So this implies that alpha power r minus s equal to 1. So alpha is a root of unity. So this complete the proof that height of alpha is 0 if and only if alpha is a root of unity. Let k be a number field with a ring of integers OK and discriminant delta k. For a conjecture that for any epsilon positive and any non-zero integral ideal A, there exists a constant C depending on epsilon, the discriminant of the field, and norm of the ideal A, such that given any pair of non-zero algebraic integers A and B, which generate the ideal A, the maximum of height of A, height of B, height of A minus B is less than or equal to 1 plus epsilon times log of the product of the norm of the prime ideas, which divides AB into A minus B plus the constant. Here the height hk of A is height of A times the degree of extension. Suppose A, B, C are non-zero mutually co-prime integers with A plus B is equal to C. Then we have height of A is equal to log of mod A, height of B is equal to log of mod B, and the same thing is true for height of C. So by taking the ideal I to be Z, we get by the phrase ABC conjecture, the maximum of log of mod A, log of mod B, log of mod B is less than or equal to 1 plus epsilon times log of the product of primes dividing ABC plus the constant. So here this is equal to radical, and by taking the exponential, we see that this gives the original conjecture due to Mazur in Australia. Assuming the phrase ABC conjecture, we prove that for almost all primes P and for all natural numbers n, the radical of tau P power n is at least the constant C divided by the radical of tau P square minus 4 into P power 11 times a power of P, where power of P is where the power is equal to 11 by 2 minus V tau P minus epsilon times n plus 1 plus delta tau P. Here the constant C depend on epsilon and discriminant of the field Q of alpha P, where alpha P is the root of the polynomial x square minus tau of P times x plus P power 11. And delta tau P is 1 or minus 1 depending on whether P divides tau of P or not. Let us compare the bounds we have for the radical of tau of P power n. As mentioned earlier, we have the following trivial upper bound for the log of the radical of tau P power n. The log of the radical of tau P power n is less than or equal to constant times log P times n. And we have the following lower bound. The log of the radical of tau of p power n is at least n power 1 minus epsilon log 2 by log n for infinitely many natural numbers and for almost all primes p. Conditionally, under the ABC conjecture, phrase ABC conjecture, we have the log of the, by taking the logarithms, by taking the logarithm on this expression, we get the log of the radical of tau of p power n is greater than or equal to a constant C1 times n, where the constant depends on epsilon and the prime p. Observe that in the upper bound we have the n. Here is also in the conditionally we have the power of n in the lower bound is equal to n, but unconditionally we have the little of 1. More generally, for a normalized Hector-Lagrange form, we prove that conditionally under the phrase ABC conjecture, for almost all primes p, the radical of the a for p power n is at least constant times exponential 1 minus epsilon times the degree of extension of kf times height of gamma fp times n for sufficiently large natural numbers n depending on the epsilon and the degree of extension of the field q of gamma fp. Gamma fp is equal to alpha p by beta p. Here alpha p and beta p are the roots of the degree 2 polynomial x square minus a for p times x plus p power 11. Observe that in the exponential, the degree of extension is at least 1, and we know that height of alpha is 0 if and only if alpha is a root of unity. So let us end this talk by showing that gamma fp is not a root of unity for almost all primes p. So let's just give the proof of the remark. Let alpha p and beta p with the roots of the polynomial x square minus a for p times x plus p power k minus 1, and gamma of p is alpha p by beta p. So we have alpha p plus beta p is equal to a for p, and alpha p times beta p is equal to p power k minus 1. So suppose gamma of p is a root of unity. We divide into two cases. The first case is gamma of p is equal to 1. Since gamma of p is alpha p by beta p, this implies alpha p is equal to beta p. So we get, by this expression, we get alpha p square is equal to p power k minus 1. So we get alpha p equal to beta p, which is equal to plus or minus p power k minus 1 by 2. This gives a of p is equal to plus or minus 2 times p power k minus 1 by 2. And observe that if we consider f to be a Ramanujan tau function, we know that the values of the tau functions are integers. Since k is equal to 12, so therefore this is not an integer, so tau of p cannot be equal to plus or minus 2 times p power 11 by 2. But in general, the coefficients are algebraic integer. So in order to prove this case, we need the stronger theorem called the Sato-Tate conjecture. By Deline's bound, we have the absolute value of f of p is less than or equal to 2 into p power k minus 1 by 2. So we can write f of p is equal to 2 into p power k minus 1 by 2 times cos theta p. Here theta p belongs to the interval 0, pi. The Sato-Tate conjecture states that these angles theta p are equidistributed with respect to the Sato-Tate measure 2 by pi psi square theta. More precisely, for any c less than or equal to d in the interval 0, pi, the ratio of the primes less than or equal to x such that theta p belongs to the interval c, d divided by pi of x is equal converges to 2 by pi times integrals from c to d sine square theta d theta. Since the singleton sets has a measure 0 from this, okay, this is no theorem due to Clausius, Harris, Taylor, Schaffer-Beran, Barnett-Lam, and Garrity. Since singleton set has a measure 0, so the integral will be 0. So from the Saturday conjecture, we get the primes for which f of p is equal to plus 1 2 power minus 1 by 2. Since we know that if f of p is equal to plus or minus 1 2 power k minus 1 by 2, then cos theta p is equal to plus or minus 1, which is equal to saying that theta p is equal to either 0 or pi. So by the Saturday conjecture, we get the set of primes p such that f of p equal to plus or minus 2 power k minus 1 by 2 has density 0. Let us consider the case 2 where gamma of p is not equal to 1. In that case, alpha p is not equal to beta p. Since we assume that gamma of p is a root of unity, so there exists an integer m greater than or equal to 2 such that gamma of p to the power m is equal to 1. So we also know that the Fourier coefficients f of n satisfy the recurrence formula f of p to the power n equal to f of p times f of p power n minus 1 minus p power k minus 1 times f of p to the power p minus 1 by 2. By using the recurrence formula, we can show that f of p power n is equal to alpha p to the power n plus 1 minus beta p to the power n plus 1 divided by alpha p minus beta p. By taking beta p to the power n plus 1 out of this expression, we get f of p to the power n is equal to beta p to the power n plus 1 divided by alpha p minus beta p times gamma fp to the power n plus 1 minus 1. Since we have gamma fp to the power m is equal to 1, gamma f to the power m is equal to 1, this gives af of p to the power f of p of p power m minus 1 is equal to 0. Now we need the following lemma due to this was independently proved by Kowalski, Robert and Wu, and Murthy. This states that if p is sufficiently large prime number, suppose there is a natural number n such that f of p power n is equal to 0, then we must have f of p is equal to 0. And in case when f is equal to f, we already proved that f of p, tau of p power n is equal to 0 implies that tau of p is equal to 0 for all prime p in the case for the tau function. Since we have f of p to the power m minus 1 is equal to 0 and m is greater than or equal to 2, so we have m minus 1 is greater than or equal to 1, so we get f of p is equal to 0. Now again, applying the Saturday conjecture, we get the set of primes p such that f of p is equal to 0 has density equal to 0. This result also follows from the result of set. Now combining these two cases, we conclude that the set of primes p such that gamma p is a root of unity has density equal to 0. These are the references. Here this is the paper where the Saturday conjecture has been proved, and this is the paper where the Below and Woody proved that n0 is equal to 30. This is the paper where the Frey conjecture, ABC conjecture, and is the paper where Lucas and Spalinki proved the unconditional lower bound for the number of prime factors of n. And here's the paper where the Murthy and Murthy show the number of prime factors of tau of n has normal order half log in the whole square condition under the GRH. Thank you for listening. Thank you.
Thank you. Thank you, Sunil. It was a lovely talk. We got a lot of stuff. Now, any questions from the audience, comments, suggestions?
Hello, sir.
Yes. Can you hear me?
I cannot.
Oh, okay.
Here, lovely
Gaurav,
sir,
can
just
you
a
hear me?
earphone.
Gaurav, can you hear me?
Yes, sir.
Okay, you could hear me now?
Yes, sir, I can hear.
Okay, okay. Thanks. So no, I was just thanking you actually, and I was asking the audience if they have any questions.
So, Hadi and Ramanujan?
No, the audience. Sorry, am I audible?
Yes, sir.
I was
Can you
asking the
continue?
audience if they have any questions.
Sorry. I cannot hear.
Yes.
So Sunil, I don't have any question. I just have it was a beautiful talk.
Okay,
Have you
thank you.
looked at the recent preprint of these RU people working with Kenono about, they say that if tau of n is equal to 0, then the number of such things, they have given a lower bound or something for it, which is like extremely small. So this is something which came out last month or something. So it's interesting that,
Recently, like tau of n is equal to, like, they classified, like, if it's it cannot take the certain values for,
yeah,
like,
that
2 times
that
odd
was,
power to power of 2.
yeah, that was the one that you said with Balakrishnan and others. But then
Yes.
there's something that came last month or maybe last to last month.
Okay, I'm not aware of. Thank you, sir.
Yeah, sure.
I'll just have it. I'll look at it.
Okay. I mean, it's on archive, I think.
Okay.
If not on archive, it's definitely there on Facebook wall of Kenono, because he has the habit of posting the new
Okay, sir.
on the Facebook. So there I saw it first. So,
Okay, sir. I'll just check it out. Thank you.
yeah.
Yeah, thanks, Atul. Is any other questions? I myself had a question on this, the height that you are using. Can you hear me,
Sir.
Sunil? Okay. So basically, it's a separate, it's a logarithmic height, right? The usual
Yes, it's a logarithm height.
different from the usual one that people use. Usually? Or maybe I'm a little bit out of touch with the material. This is the standard height that's used in number.
So I use the sir, tell me, sir.
Oh, sorry, you cannot hear me.
Yes, sir.
No, is it the standard height that is used in number fields? Is what I was asking.
This is the way I use this expression so that I can the norms and this log of it. So I use this expression. This is same as that. This can be from the definition of height. You can deduce this this expression.
Oh, okay. Thank you. And this Frey was actually giving a lower bound. That was a little unusual, right? So even in the ABC case, if that translates
Sir?
to a lower bound for the radical?
Yes, sir. It gives a lower bound for the radical in terms of the absolute values here.
I see. Okay. Sorry. That was a bad question. Okay. I get it. Thanks. Fine. I'm done with
Yes.
my questions.
Here we get the radical.
Sure. I get it. Sorry. It was a bad question. May I request anyone else from the audience if they have any questions, comments?
Can you hear me?
Yes, sir.
Yeah, Sunil, yeah, it was a very nice talk. So
Thank you.
I have one just quick, like you have mentioned one result that tau n equals to prime p for a fixed prime, that I think Murthy and someone else, yeah, they have proved that that's a finite set, right?
Yes, if for an odd prime.
Yes, for an odd prime. Okay, so is there any similar result, like if like when tau of n equals to minus p? Like you have mentioned another result like tau n equals to plus minus
Okay.
1. There is no. I think that is there is no solution if tau n equals to plus minus 1. So I was just wondering that if there is any such result.
Actually, I stated for the prime p here, but the same thing holds for the minus p.
Okay, I see.
Let me go to the slide. Here, I just take the prime p on p. I didn't consider that. Even we can take the modulus of tau of n is equal to p. This
Okay.
precisely follows from this result. Here I stated the result from which it follows.
Okay.
Here, this follows from this result.
Okay. I
If tau
see.
of n is odd, then
I see.
modulus of tau of n is greater than or equal to log n to the power p.
Okay, I see. I see. And similar kind of result has been done for other Fourier coefficients as well. Like a Fourier coefficient of other Hecke eigenform. This instead of tau n.
I think for the if you assume the quotient to be integers, we can deduce, and there is a otherwise we have to instead of, because here these are integers, we have to use the modulus. Otherwise, you have to take the heights of the Fourier coefficient.
Okay, I see.
So we get a lower bound for the heights of the Fourier coefficient.
Okay. Okay, good, good. Okay, thank you, Sunil.
Okay, thank you. You can look at the that's a paper by Bhan, Gun, and Rath, where they generally prove for the Hilbert modular forms in terms of height.
Okay, I see. I see.
Yeah.
Thanks.
Okay.
Okay, could we have more questions? Okay, if not, we thank the speaker once again for this enlightening talk. Thank you.
Thank you, sir. Thank you very much.